Good afternoon. Everybody hacking here? Hands up for hackers, yeah? So I am too. I'll be excited to see all your guys' projects. Please feel free to come say hello. Today I'll be talking about tangible zero-knowledge data from a non-PhD. I am the non-PhD, Brian Wilkes. You may know me by Outsider Analytics. So what's on the docket for today? We're going to look at how zero-knowledge is used on Ethereum, how to find zero-knowledge proofs on-chain, and specific ZK project characteristics and what they mean. So this talk comes from a grant I received from the Ethereum Foundation Privacy Scaling and Explorations team. That I did this talk in DevCon as well, so you stole some of the graphics, as you'll find. So we're not going to go over Waldo. Sorry, Waldo. I did make that graphic myself. But we will go over some quick, brief overviews. So what are zero-knowledge proofs? You have Alice, you have Bob, as is standard, and Alice wants a drink. Bob says, how old are you? So Alice provides the birthday into the zero-knowledge circuit, which then produces a proof over to Bob, who's the verifier. And then, assuming that it's correct, alcohol will flow to Alice, who can change the state of her sobriety. So the important thing to know and how this translates over to actual on-chain Ethereum is there's a prover, there's a ZK circuit, there's a proof, and there's a verifier. And no alcohol. So if we're going to, let's look at one of the first applications here, which is scalability. So obviously, Ethereum does about 13 transactions per second, and we need to scale that up significantly to be able to do transaction settlement for the world. So let's assume that we have a layer 2 blockchain. This layer 2 blockchain is producing blocks independently, and what you do is you can take that blockchain's state and you can put it into, as an input, the zero-knowledge circuit. That will pop out as a proof, and then that proof will be given to the verifier smart contract on the Ethereum main chain. So then the layer 2 state source of truth will be updated, assuming that that proof is true. Moving to privacy. So obviously, as a data scientist, we can find a lot of stuff on chain, and if you know the addresses. So we need to have privacy before we can really move to mainstream. So the way you would utilize zero-knowledge proofs to be able to provide privacy on chain is you would have a secret, you would put that into the zero-knowledge circuit, and then that proof that came from there would then be put on chain in the verifier smart contract, which then would release funds in circumstance like Tornado Cash. So now that we know generally what they are, here let's actually talk about where they are on chain and how you find them. And I did build this as well. So now, the search for verifiers. We are going to search for verifiers on chain. How are we going to do that? So the important characteristics of a zero-knowledge proof are in the circuit. Why is that? Here's a good example of ZK Sync V1 for 1 week in September of 2022. It produced, in that week, 2,070 blocks, or 2,170 blocks, 265,000 transactions, which were batched into 214 inputs. Those inputs went to the zero-knowledge circuit, which produced 214 proofs, and those proofs were then verified on-chain with the verifier smart contract. So each circuit has a unique verifier on-chain. So if we're going to use public blockchain data, how do we find those verifiers that represent the circuits on-chain? So we'll go through some tools. So the first tool we used was BigQuery. I tried doing it, wasn't quite fast enough. So BigQuery is a system that you can go on, and it has public blockchain tables from Ethereum layer 1. And on there, I used contracts, traces, and transactions. Those tables, which you can query on BigQuery using an account. So the first thing I did is I searched through the bytecode for contracts, and in that bytecode, you can search for constants directly, because those are put in as a hash. So that hex for the contracts or finite fields is this big-ass number right here. It is very unique, and it's only used for finite fields of doing modular math for cryptography. So after searching through that, I found 584 contracts with that finite field constant. So I checked every one of those on Etherscan, and most were not verifiers. So moving on, we went to what's called the transaction decoder. So this is a tool, I think, are there any data scientists in the crowd? Anybody? Yes, that's what I'm talking about. I'll talk to you specifically. So the transaction decoder is a really useful tool from Etherscan if you want to know what a transaction is actually doing. So here, it's the transaction decoder, and then it shows at the bottom what the execution trace is. So the execution trace for this ZK sync block proving is, first it takes the proof, it goes into the prove block section, which then goes into the verify aggregated block proof function, and it produces true at the end, which means that the ZK sync v1's state can be updated on layer 1. So utilizing that data, you can use method IDs to try and find things that have happened on chain. What's a method ID? So the method ID is the first 4 bytes of input data that's put in for a function or a trace. A function or a trace for transactions or traces. So let's take an example. This here is the fry statement for Starkware. It verifies a fry. So if you take this function, take out all the names of the variables in white space, and take the first 4 bytes, the kcac 256 hash of that, then the method ID is this in red, which is the same as the first 4 bytes, which is in the input data. So you can search through a bunch of data using whatever those function IDs are. And the method IDs are also on a public database called 4byte directory. It's an open source project, and it's great if you want to know what's actually happening. You can put in the byte signature, and it'll pop out what the text signature for that function is, if it has it. So what did I find? I found 96 confirmed verifiers on main chain that had verified 763 times. So I think you can see it kind of, the verifications do a little bit of a downturn once Tornado Cash got sanctioned pretty hard. But these are the 16 active contracts from those 96 on Ethereum main chain. I know they're too small, but I will show you a QR code later you can look at, and I will go over this, I promise. So let's look at their characteristics. So the first thing we'll look at is what proving systems they'll use. So these are the proving systems that are snarks. You have Groth16, which is being used by Tornado Cash and its forks. You have Hermes, you have Loopring, and then you have Plonk. Plonk is used by ZK Sync, ZK Space. And then you have Ultra Plonk, which is used by Aztec. You have Halo 2, which is used by Scroll. And then you have the Starks, and Starks are being used by, as you can imagine, Starkware. So all the Starkware projects. Snarks apparently are going to be in trouble when quantum computing comes out, but we don't know when that will happen, so the UFOs might get us first. Trusted setups. Let's look at what trusted setups are first. So it's where on the elliptic curve the verification and proving is happening. So we won't get too deep into that, but basically you use an MPC, multi-party computation ceremony to be able to prove or provide a secret on chain. So how many of you did the KCG ceremony commits? Yeah, we did some. So we're going to do one soon. It's a big ceremony to allow proto-danksharding within Ethereum. We're actually going to make a big-ass explosion and measure it and then put that on chain as a secret. So hopefully that'll go well. But that is an example of a trusted setup that's being done with multi-party computation. I like to think about this as a nerd, which is as Thanos in the Infinity Stones. So if Thanos gets all the trusted setup pieces of secrets, then they can wipe out the universe of your trusted setup and they can go and attack your proof. So you want at least one of those stones not to get into his hand so that you can continue to have a secure protocol. So what trusted setups are these different projects using? Groth16 uses a 2-step trusted setup. The first step is the perpetual powers of tau, which is on Ethereum, and then the second step has to be unique for each unique circuit that's being verified. This was improved by Plonk and Ultra Plonk and all the other Plonks that are out there, and that is essentially it's a single universal setup. So they did one ceremony, and everyone can use that ceremony for any Plonk circuit they write into the future. And then Halo 2 and Starkware, in the Starks, they can use no trusted setup at all as long as they're set up in certain ways. So what the projects are, hopefully you guys can see that, but we have Loopring, Polygon Hermes, and Tornado Cash. We're using Groth 16. These were the perpetual towers of Tau plus a step 2. In that step 2, Loopring had 16 participants, Polygon Hermes had 6, and Tornado Cash had 1,114. So if you got all 6 Polygon Hermes participants' secrets, you could break Polygon Hermes, which I think they're moving to ZK EVM, so it's no big deal anyway. Moving on, if you want to do Plonk, all of them that are in production have used Aztec's Plonk universal setup. So all of them use the same setup. You can go on GitHub and check it out. It's pretty cool. And there are 176 participants for that ceremony. And then you have your Starks, which is StarkX, in your Starkware projects. Those did not have a trusted setup because they're Starks. Recursion. So another thing that people are trying to do when they build these different protocols is build in recursion. Recursion is basically the idea of taking a bunch of individual proofs and recursively proving them up in one. So why do you want to do that? You need to be able to do parallelization of proofs so that you can decentralize proof generation. It also allows you to chain proofs, so you have from the beginning, the input for one proof can be the output from the previous proof. And then also it can reduce the proof and verification size. So Groth 16 cannot do recursion, and everything else can, as long as they make the implementations full. So Halo 2 is a little difficult at the moment, but why does anyone use Groth 16 if it is so difficult in these ways? It's cheaper and it's faster. So a lot of implementations will use Groth 16 on Ethereum, but use a bunch of other protocols beforehand in order to actually get to that final proof. So data availability, we'll talk about this next. Once again, as a data scientist, I love this kind of space, but we can talk about what the zero-knowledge layer 2s are doing. So your first type of layer 2, if you're not too much of a purist, is the ZK Validiums. So they have their state root is on layer 1 in a bridge contract, and their state reconstruction data is not on chain except through a data availability permissioned committee. So the difference is ZK rollups have their state root on Ethereum layer 1, but their state reconstruction data is also put on layer 1. Why would you use ZK Validiums versus rollups? Many more transactions per second can be done. So who's a Validium? That's your StarkX projects like IMX, Runify, SoRare. You have ZK Porter, which I don't know if it's actually coming out, but it's been talked about many times. You have rollups, which are DYDX, Loopring, ZK Sync V1, ZK Space, StarkNet, ZK Sync V2, Scroll, all the polygons, and then all the ZK EVMs that are coming out from everyone. So let's talk about force exits from rollups, what it actually means to be able to get off of rollups. So this is a circumstance for how you would look at a layer 2. You're the user here and you're happy. You put a transaction through to a very nice validator or sequencer, and they put your transaction into the layer 2. The layer 2 puts it through a ZK circuit, produces a proof, and puts that into the Ethereum layer 1 bridge contract. But let's say your validator or sequencer becomes evil. Then you can submit your transaction directly to the Ethereum bridge contract. And if the sequencers don't include your transaction within a certain period of time, then the bridge freezes and you can produce a proof yourself using the ZK circuit to get your funds back off that bridge. Now, this is a great system, except it does cause for some issues. So if you want this to work, in order to inherit the full security, a rollup has to have available data on layer 1, functional, accessible force exits, time delays for the layer 1 contracts, because if they can change the contract, then they can kind of freeze your funds. And then fourth would be the layer 1 locked funds have to be equal to the market value on layer 2. So there's nuance to this, but generally, if the validators and sequencers become evil, then what the value you can bring back by force exiting has to be all on layer 1 Ethereum. So if it's on layer 2 and you have native assets that are significantly more valuable that are being brought down to layer 1, then those assets are not fully protected by the rollup structure. So, well, that's pretty much what I have for you today. I'm hoping you guys will be willing to get into the data a little bit. So BigQuery is a great source. This is the project GitHub that I did with the Ethereum Foundation PSC team. L2Beat is, of course, just a wonderful resource that I'm sure everyone has used at this point. And then we are actually doing a hackathon that's going to be a lot of data availability and help people understand what data is happening on chain for a lot cheaper and faster. And if you need that or you're doing your hackathon through it, then please reach out to me. We'd love to talk. Thank you. So I'll give some thank yous out to the Daily Gwei, Discord, and all the people there are so helpful. It's amazing. We have the ZK podcast is a great resource. I'd highly recommend it. L2Beat, once again. You have the Ethereum Foundation privacy scaling and exploration team. Specifically, Justin Martin has been extremely helpful to me. And then thank you, Mark, for all your help on this. Absolutely. So that's what I got. Thank you very much for your time. I really appreciate it.